And we'll wait for OBS to turn on. It's on right now. All right. So what we'll do today is to talk about one of the three instructions. You have a new lab today, and in the new lab, you're gonna play with one of the three, well, actually three of the three instructions that has to do with how do we put something into a register. Last time we talked about the subtraction instruction, which assumes whatever we want to subtract is already in the registers. So how do we get something into the register to begin with? So that's kind of the question that we'll answer today. So just like last time, I'm going to write some simple code, and then we'll track down how the processor executes those instructions. So it serves several purposes. It illustrates what the instructions do, but more importantly, it also shows you guys how to analyze the processor architecture. So if I give you a brand spanking new instruction and I don't tell you, if I don't explain to you how it works, you can figure out how it works by yourselves. Okay, so that's kind of the objective, the kind of like the dual objective of today's lecture. Before we start, do we have any questions? Any questions about the assembler? Any questions about running the program inside the inside LogicSim? No questions about the process? Okay, all right, very good. All right, so if there are no questions, we'll go ahead and take a look at a few instructions first, and then we'll go ahead and actually do some coding. So this is kind of where we start coding, even though it's very primitive at this point. So I'm going to go back to the processor and then go back to the opcode table. And this time we'll pick one of the load instructions. Let me magnify a little bit first so you can see a little bit better. So here's a load instruction. So with this load instruction, from the C description or the description in C notation, you can see that it's treating Y as a pointer. Okay, so register Y, which can be one A, B, C, or D, is being used as a pointer. And whatever Y points to, the content at that location in RAM is used to copy into register X. So that's the load instruction. When you look at the syntax, whenever we, whoops. All right, it just got updated, and that's why it wants to pop up and go like, woohoo, we got a new version of tree style tab, which is really a great tool, but I don't like it when it intrudes in my instructions. All right, so whenever we dereference, instead of using a star or asterisk, which is what you use in C, in assembly language, it's kind of conventional that we use parentheses to indicate we are dereferencing that component. Okay, so when you see parentheses, that usually tells you that we are dereferencing, especially what is inside the parentheses, is a register. All right. So LD has two friends. One friend is called ST or store, which goes the exact opposite direction. Look at the C description here. This one dereferences Y, but it's on the right hand side, but it stores the value onto the left hand side. The other one, which is the ST instruction, that's exactly the opposite. Register X supplies the right hand side of an assignment, and then whatever Y points to is what is going to, it specifies the location in RAM to store the content, store the value. So are we doing okay so far? I'm hoping everybody has some exposure to pointers and understand what asterisk means in a C expression. Is that okay? All right, okay. So there's one more, right? Because I said LD has two friends. This is one. So the other friend of LD is LDI. So let me see, where is LDI? It could be above, could be below. And it is... Oh, I skipped it? Oh, there we go. Okay, so this is LDI. LDI is kind of an awkward thing, okay? So when you look at LDI, it says, X equals 2, and then we have a dereference on the outside of the parentheses, And then we got PC++ in the inside. What does that mean?
Is that the program counter?
PC is the program counter. Very good. Okay, so it's post incremented, right? So that means whatever the program counter is pointing to is what we retrieve. And that is being stored into the register X. And then after that, the program counter is incremented. Okay, so this is the first one that we're going to look at today because this is the only way for you to initialize a register with a constant. Okay, once you have a constant in a few registers, then you can do calculations. Okay, you can add, subtract, compare, whatever you want to do. But we need to get some constants into the registers first, and this is the only way to do it. So are we okay so far? Does everybody know what we are about to do today? Yes? Okay, excellent. All right. And the room is fortunately getting a little bit warmer, especially because we got more people in the room. Each person is about 200 watts when it comes to thermal output. So, with, I would say about 20 people, we got 4,000 watts of thermal output just because of the people. That's a lot of power. Of course, when we start jumping and actually walking or cycling, we can have up to like 400 to 500 watts, depending on who that person is. Okay, so let's go ahead and play with this, which also means the first thing we need to do is to go to the assembler. Okay. This is the assembler with postfix expressions, which is the one that we are supposed to use. The other one would work, with most of the stuff, up to this point anyway. So right here, I got some junk stuff here. So first thing is to delete all of the junk. Okay. So one thing is, you want to use the delete key to only delete content of the cells, but do not use any other mechanisms to get rid of the cells. Okay, so let me just kind of be more clear about what I am saying. So when you want to clear something, do not delete cells. Okay, this is not what we want to do. Do not delete the column. Okay, what you want to do is simply press the delete key to only remove the content. Because if you choose any one of these options here, it's going to mess up the spreadsheet. Then you have to download the spreadsheet again. So we just press the delete key, get rid of all the stuff. The other thing is, do not double click before you paste code in. Okay, if you double click in a cell first, like this, when you see the blinky cursor, and then you paste from a notepad, it is going to paste all the code into one cell, which does not work. Okay, so if you have multiple lines to paste from an editor, make sure that you paste when you do not see the blinky cursor. Is that okay? Because I saw a few people do that, in the lab on last Thursday. Okay, so I just want to tell you, okay, that does not work. Okay, so we'll do something simple first. So this is LDI, and we'll pick a register, let's say register B, and then we specify an expression that evaluates to a constant. So that means it doesn't have to be a single constant. It can be like 23 plus 45 and so on. Is that okay? So let's go ahead and give it a try. So 23 plus 45, this is how we write it. It is called the postfix notation. The reason why we use postfix notation is because TAC is lazy. Okay, because what it takes to parse infix notation is a bit more work compared to parsing postfix notation. So if you want to use something like this, which we'll all gonna do later on in this semester, you have to learn how to do postfix notation, otherwise known as RPN, reversed Polish notation. You can Google that, you can YouTube it, and there are tons of material to teach you how to do it. If you have an uncle, okay, or I guess even grandparents or relatives, they might know how to do it too, because a long time ago, this is what HP calculators could do. They can only take RPN and not infix notation. because the calculators had very. I will explain how to do postfix notation, but just for the sake of showing you that the assembler takes postfix notation, this is what I'm going to do, and then we'll follow up with a halt instruction right away, so this way the program stops, okay, and we can tell the program has stopped. Are we doing okay so far with this part here? Okay. Does anyone want me to talk about postfix notation a little bit more, or do you want to just kind of move on and talk about LDI? Because I can do a little bit. Yeah.
Just a little bit.
Okay.
Is every symbol allowed in postfix notation?
The full syntax is described in the assembler manual. So if you look that up, it will tell you, it will accept, addition, subtraction, multiplication, and division. Okay. So all the major math operator, but it doesn't support bitwise operators, for instance. Not yet. I mean, I can make it so that it does, but it currently does not. Okay, so let me just explain postfix notation a little bit. Okay, so the best way to do it is to use a blank editor. So let me go start mousepad. Where's mousepad? There we go. And of course, it has to start it from a different desktop. Okay, there we go. All right. So typically, when we write stuff, we're taught to only use infix notation. So I'm going to use just constant, symbols here. So if you want to say A plus C and then the whole thing times B, okay, this is how we write it. And you can see that you need to use parentheses in this case because the default priority of the operators is so that the addition has a lower priority compared to multiplication. Without the parentheses, I would have computed the product of C and B first, and then add that product to A. Okay? But with the parentheses, it clearly indicates that we have to add or we have to compute the sum of A and C first, and then we'll multiply B to that sum. Is that okay? So this is something that we have to get used to in infix notation. In postfix notation, this is going to be written as AC plus B times. So the way it works is it is based on the concept of a stack. So whenever you see a value like A, C, and B, it is pushed on the stack. Whenever there's an operator like plus or multiplication, it will pop the number of items that it needs. Like in this case, both operators need 2 operands, right? So it's going to pop 2 items from the stack, perform the operation, and then the result of the operation is pushed on the stack again. Are we doing okay so far? Yep.
It doesn't matter how many variables are stacked. You can literally have like A through C or whatever. It'll have a plus.
Well, in this case, I'm using ABC, to represent values. So they're not actually. So we don't use actually ABC in the assembler. Oh yeah, you can just add a whole bunch. Yep.
So if we had DAC plus B asterisk, D wouldn't be touched because it's not included in the stack that's being
That is correct.
modified? Okay.
You can leave an item on the stack that is not touched, but then it's just not used, right? So that usually is not a good thing, that you're not consuming everything on the stack. Okay. Yep.
Follow-up question: how do we do stuff like exponents in this?
You will need to define an exponent operator. Like using the caret symbol, for instance. So you would need. So every operator needs to have a symbol to represent it. The parser that I implement into the assembler is relatively simple, so it doesn't do power or anything like that. It doesn't do shift either. I could add additional operators, but at this point I'm not doing that just yet. Okay. All right. So the way this works, how many people have taken 430 and understand what a tree is? Okay, we got a few people, and how many people are taking 430? Okay, we got a few other people. Okay, very good. So I'm going to use this, so you don't have to write this down because it's not going to be in a test. But if you understand what a tree is, it really helps a lot. Okay. So for instance, with a plus c, the whole thing times b, we have the multiplication on the top as the root of the tree. B is on one side, and then on the other side we have the addition with a and c. Okay, so this is just a hierarchical view of the operation. Whether it is infix or postfix does not matter. Okay, because this is telling you how the expression is structured. Okay, does it make sense? At this point, even for people who have not taken 430, that we can represent the operations in this hierarchical way. Is that okay? So once you represent everything as a tree, postfix is a post-order traversal of a tree. Is that okay? Now that is kind of, it takes a little bit more explanation in this case. So a post-order traversal means you're traversing the left tree first, and then you traverse the right tree, and then you go back to the node itself. Okay, so I'm going to show you what that means. So we start here. Okay, this is where we start, but until there's nothing else to do, you don't do a single thing about the operator itself. So this is the first thing that we see, and then we traverse the left side. So this is the second thing that we see, but it's not a leaf. It is not at the end of a tree. So we go to the left again. This is 3. Okay, so when we get to this point here, when we get to 3, we say, hey, A does not have any subtrees under it, right? So we have to quote unquote process it. The way we process A is simply to push it on the stack. Okay, then we go back to the plus. Okay, this is step 4, and we ask, have we processed everything that is under this particular node? The answer is no, because at this point we have only processed the left tree, but we haven't processed the right tree. So then what we do is we go to the right tree and say, okay, we'll process C at this point. C is a leaf node, which means it does not have any subtrees under it. Okay, so that means, okay, we don't have anything to do at this point or anything further to do with C, so we push C on the stack. So at that point, you have A and C on the stack. Is that okay? So from C, we go back to the plus. So this is step 6. This time, when we go back to the plus, we have processed both the left and the right subtrees, which means, oh, we are done. Okay, we're done processing all the subtrees. So the post traversal says, when you're done with all your children or all your subtrees, then you process yourself. So at that point, at step 6, we have AC plus in the expression. Then we go back to the multiplication symbol, which is step 7, and we ask the same question. Are we done processing all the subtrees? What do you think? No, because we are done processing everything on the left-hand side, but we haven't done a single thing to whatever is on the right-hand side. So what we do is to say, okay, let's process the subtree. Go to step 8. When we get to step 8, B has no subtrees because it is a leaf by itself. So by step 8, we have A, C plus, and then the B, also expression. Is that okay? Then we go back to the multiplication, which is step 9 in this case. This time when we get back to the multiplication, then we ask the same question. Are we done with all the subtrees? Yes. So it's time to process myself. It's time to process the node itself, which means at step 9, the postfix notation is done. Is that okay? So as long as you know how to draw an expression, in infix notation, using a tree representation, by traversing that tree in a certain way, you know how to generate the postfix notation. Yep.
For a processor, is infix or postfix faster usually?
The processor does not have the concept of infix versus postfix. That is a concept that is only needed when you write programs. So by the time the processor processes information, it will need the operands to be in registers, and then it executes whatever instruction that you need to do the actual processing or the actual calculation. So the processor, I would say, if you look at it that way, is inherently postfix type because you need to get the operands ready first before the instruction to do all the calculations. So the processor natively actually does quote unquote postfix style of ordering. But we are taught infix notation early on, from like kindergarten. So that is why, it seems foreign to us. The postfix notation looks foreign to us, even though it is actually an easier way to represent expressions. It's just like base 10 versus base 2. We have been poisoned by base 10 for this long. And then now we look at base 2, which is a much better base to use, and we go like, it doesn't make sense. It's almost like you live in a region where you have daily air pollution, so you're used to all that pollution, all the dust and whatnot, and then you go to a forest with all the clean air and whatnot. They go like, ew, clean air, that is so bad. It's kind of the same thing. Postfix is kind of the same thing too. So are there any questions about postfix? No? Does anyone think that postfix may have some application beyond the scope of this class? Okay, I got one person and one little nod and go like, maybe. Okay, so postfix notation is actually important past this class. Why? Because how many people have heard of PS, postscript? It's a printer thing, right? Okay, you go buy a printer, and a lot of times, except for HP, the printers will say, "Oh, we recognize blah 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 script." Okay, those are all derived from PostScript. And why do you think PostScript is called PostScript? Script is easy, right? It's a programming language of sorts. Okay, but why Post? Because you specify everything in postfix notation. That's why it is called PostScript. Okay, so then you ask, but we don't deal with PostScript, okay? Because most of the time we just install the correct driver for a printer, and then we just say print or Control P, press the Enter key, and you're all set, right? What about PDF? PDF stands for Portable Document Format, right? Who makes PDF? Which vendor invented the PDF standard? Adobe, very good, okay. And guess who invented PostScript? Adobe, exactly, okay. So what is the purpose of PDF? For the most part, go ahead. Give Adobe money, okay, but I'm using open source and I don't give Adobe a single penny. Okay, but what is the purpose of PDF? Okay, on a daily basis, you download the PDF and then what do? You can print or you can display it on the screen, okay? PDF works the same way as PostScript in the sense that it is not a raster, it's not a bitmap of what you see, it is just a whole bunch of instructions. Go over here and draw an arc up to here, okay, and then change the thickness of the pen and then draw a straight line from here to here. It is a whole bunch of instructions to draw something on a medium, okay? PostScript is mostly designed and used to draw something on a piece of paper. PDF can be done on the screen, okay? It can also be done on a piece of paper. But when you look into PDF, okay, when you look into a portable document format file, okay, it really is PostScript underneath. So once again, PDF is PostScript based, or I should say postfix based. So if you understand how to do all this stuff here, you'll be able to understand, once you open up a PDF and then look at the actual scripting in the inside, you will understand what it's trying to do. Yep.
Are there any C family languages that use PostScript?
No, unfortunately, no, because I think a programming language is designed so that more people can use it, and to have to learn postfix first, is apparently an obstacle to a lot of people. But it is really not a big obstacle. You can get used to it pretty quickly. The idea is you just need some practice. Now, the natural question that some of you have is, well, how complex of an expression do we have to deal with in this class so that we have to learn how to do all this stuff here. Most of the time, you're just adding an offset to something. So the most you do, with, I wouldn't say everything or for the entire duration, but most of the time you just need to say, I just need to add it to some constant of A. So if this is the infix, what is the postfix? A2 plus. Okay, very good. And I think we can all manage that. Yes? Okay. So just remember, it is in postfix notation, because if you try to enter something in infix notation, it does not work in the assembler. Okay. So that's a little short introduction to postfix notation. So the first thing we want to do is to say, well, tag, you can say whatever you want, but is it actually doing postfix notation here? So what we do is we switch to the assembler tab, and then we try to see what code is generated here. So this one is generating 6D and 44, and then the halt is 01, which we already know. So the question is this 44 in hexadecimal representing the sum of 23 and 45? What do you think? Well, first of all, this is 44 in hexadecimal. What is the decimal representation of that value? The 4 is the left 4 would be the quantity of 16s. The right 4 would be the quantity of 1. The quantity of 1. So we have 4 times 16, which is 64, plus 4, which is 68, right? Is 68 the sum of 23 and 45? Okay, so I think it works, okay? So this is also an interesting moment, because we can see that the LDI, a single LDI instruction takes up 2 bytes. You can see the first byte is 6D and the second byte is 44. So why is that the case? So we switch back to the opcode table first, and then we look at the LDI instruction. It has a bit pattern of 011011XX. In this case, the XX would be 01 because we are specifying register B. So that means the entire thing is going to be 0110, which is a 6 in hexadecimal, 1101, which is a D in hexadecimal. So 6D is actually correct. So now the question is, what is the other byte? The other byte is exactly the constant that we need to copy to the register. Is that okay? All right? Okay. So now the question is, but how does it work? So what we'll do is we are going to go back to the assembler, and then we go to RAM file. Make sure that RAM file sets v2.0 raw before we download as a CSV, and save the file. I'll put it into my temp folder. We'll call this ldi.csv because it is that instruction. And then I switch to one of my trying to find one that's easy to look at. This one is good. So now we start up Logisim. We go back to the processor file, and I'm going to go to one that is already pre-installed, which is here. There we go. We go to the RAM component, right click on it, and then we load the CSV that we just created. Now with something this simple, it is actually, it will take you less time just to type it in than go through all this process to load it in. So we load from /tab/ldi.csv. So then we got the program in, okay? So if you just want to look at the end result of executing this instruction, we can just turn on auto-clicking and just watch it until we get to the halt instruction. But that would defeat the whole purpose of today's lecture, because I want to analyze how the instruction gets this done step by step. Okay, so that's what we need to do. Now, because I just started Logisim, it is already in the initial state. I don't have to reset it at any point. I don't need to reset it now. So what we'll do is we'll start the taking, right? Control T and stuff. When the microcode pointer is 0, 0, 0, and you have a rising edge, that is called fetch, okay? Because what we are doing is we are retrieving a byte from RAM, and the program counter is telling us where to go, and we're retrieving that byte into the instruction register. This is something that we went through on last Thursday already, so I'm not going to go through the details of tracking everything down. I'm just mentioning it so that we know this is called fetch when we execute an instruction. And we can double check, okay, so we can zoom out a little bit. There we go. And we can see the instruction register is now 6D, which is the opcode that we just specified. Is that okay? The falling edge is going to increment the microcode pointer, so we get to location 001 in ROM. This part does not have any particular name other than just auto-incrementing the microcode pointer. Okay, so you can see how the microcode pointer is now pointing to location 001 in the ROM. So now we're going to have another rising edge. With this rising edge, what we are doing is we are auto-incrementing the program counter. So if you keep an eye on the program counter will be incremented to the next available location. Last Thursday, I did not mention this part too much because auto-incrementing the program counter just seems to make sense, right? Because the content of location 00 in RAM is already loaded into the instruction register. There's no need for the program counter to point to location 0 anymore. We should point to the next location so that we can grab the next byte. So it seems to make sense, right? So if I do a control T right now, which is a rising edge, you will see the program counter will go from 00 to 01. So that we'll be ready to go to the next location in RAM. Okay, there we go. But for this particular program, it is particularly important. Because remember, the LDI instruction says it wants to do a PC++ and then on the outside do asterisk, right? The PC is referring to this PC. In other words, we are ready to go to location 01, grab whatever's at that location, and put that into register B in this case. Are we doing okay? So this is important because we have to remember that there's an auto increment of the program counter once we grab the opcode. Right after the fetch, we auto increment the program counter so that by the time we get to the microcode content that is specific to LDI, the program counter is already pointing to the correct byte. Are we doing okay so far with that? Yes? Sort of? Okay. So now we're ready for a falling edge. This falling edge is called decode because what we are doing is we are copying this 6D into microcode pointer. But we are not just copying the 8 bits. We're also padding 4 bits to the right-hand side. So the 4D becomes 4D0. Okay, we talked about this last Thursday as well, so I'm not going to go into too much detail. But this is called decode because, just observe. It's called decode because now the microcode pointer is pointing to a location in ROM that specifies all the bits that I need in order to actually perform the operation of LDI. So the rising edge, rising edge, and falling edge, those 4 edges were only to set up to get here so that we can get to the bit pattern that is in the ROM that is specific to LDI in this case. Are we doing okay so far with the exercise? Are there any questions? Yes?
So for using LDI, it's always going to go to 60O or?
No, because it will go to 6D only because we are specifying register B. Because remember, it's 0110 11XX. Which means that XX can influence It can be 6C for A, register A, 6D for register B, 6E for register C, and then 6F for register for register D. Okay, so you have to be careful with that, because LDI specifies a whole family, like a family of 4 individual opcodes, 1 opcode per register, because we got registers A, B, C, and D. Okay. All right, so once we get here, what do? We analyze the processor and find out what is going to happen when we have a rising edge, okay? Because right now the clock is low, right? When the clock is low, that means when I do Control T again, it would be a rising edge. All components except for the microcode pointer would are sensitive to rising edge instead of falling edge. So now we want to find out what is going on here, which means you will have to go through the whole processor and find out what is active. And a trick to do that is to follow all the bright green lines. So when you look at RAM, the RAM component, this time we have to ask a few questions, because RAM cell is a 1. So the RAM component is selected, which means it's paying attention. We think it's going to do something. So as soon as you have the RAM component selected, there are naturally 2 questions that you have to ask right away. One is, are we reading or writing? Okay, what do you think? We are reading, because when LD is a 1, we are reading from RAM, okay? And the second question is, where are we reading from? Well, you can tell right away visually, okay? But the question is, what is telling the address port of RAM which location we are interested? So now you have to track it down. And the way you track it down is to follow this wire, or this net. It goes back to a multiplexer. So according to this multiplexer, which input is connected to the output? Input 0 or input 1? What is the select? What is the value of the select? Is it 1 or 0? It is 1. So input 1 is connected to the output for this particular multiplexer. So I'm going to track down the wire or the net connected to input 1 of this multiplexer. Okay, where does it go to? It goes to the register, right? It goes to the output of a register. And which register is that? It's the program counter. Okay, so the program counter is telling us which location in RAM we're interested in. Wait, we call that asterisk PC in C and C++. We're dereferencing using the program counter. Is that okay? Is this configuration connecting with what you understand in C and C++ about the dereference operator? Yes? Okay? Because this is important, okay? Because I'm trying to make a connection between things that you already understand, which is the dereference operator, and things that we're introducing at this point, which is there's a register connected to the address port of RAM. That is dereference. Is that okay? All right? Cool. So we have answered 2 of the questions, which also leads to the third question, right? Because we're reading from RAM at a location that the program counter is connected to. The question is, what are we doing with the data port? Because the data port of RAM is now an output from the perspective of the RAM component, which means we are hoping that somebody is paying attention to the data bus so that that content is used somehow. Does that make sense? Okay, so we'll try to figure that out. So we'll figure out by tracking down this net. Now this net does go to a lot of different places, but we only have to pay attention to the places where something is enabled. Okay, so we can track this down. Okay, it goes down here, but you will see that the instruction register is not enabled. Okay, so it's not going to do a single thing. The instruction register will maintain its content. Okay, no big deal. Where else does it go? It goes to the output of this demultiplexer. Well, you have to kind of pay attention, because if this demultiplexer is enabled, we might have a bus fight, because this demultiplexer may want to put a different content onto this wire compared to what the RAM is trying to specify. But fortunately, the demultiplexer is not enabled. So it's not going to do a single thing. Okay, where else does this net go? So we just track down the highlighted wire. It also goes here, okay, and also here. Well, let's track down this one first. This is a multiplexer. What is selected with this multiplexer? 0 or 1? 0. Okay, so input 0, which is from the data port, is now connected to the output of this multiplexer, which goes into the input of the register bank. Okay? Is the register bank enabled? Is it ready to update something? Well, input enable is a green, light green, which means it's a 1. So yes, we are about to update a register. Which register? Well, it's a little bit harder to see from here. Let me see if I can poke this wire. If I can, we can see it. And we cannot because it's too close to the register bank component. So we go into the register bank component. It's selecting register 01. And which register is that? It's register B. Okay. And you can see actually the bright green wire is telling us that register B is now enabled. We doing okay so far? So the 44 is in the register input port because 44 is 0100, 0100. That is going into the D port of register B. Register B is enabled. So on the next rising edge of the clock, register B will update to 44 as its content. Does that make sense? Okay. Okay, so that seems to be consistent with what we thought LDI would do. Yes? Because we remember the C expression is, it would be equivalent to something like this. It would be equivalent to register B gets whatever PC++ the reference is going to provide. So far we have done all this, right? We have looked at the program counter. It is driving the address port of RAM, which means we are dereferencing using the program counter. The content of that location, which is this part here, is going into the register bank, and register B is the one that is ready to update. So far we have all that, except for the plus plus. Is the program counter going to auto increment at this point on the next rising edge? That becomes the next question. Okay, but before we go back out, we do want to double check and make sure that register B is about to update to 44 as its new content, and it is in fact selected. Okay, so we just want to double check. So as soon as we have the rising edge, register B is going to update. But now we go back to the main and we ask the question, is the program counter going to update an auto increment from 01 to 02? That becomes the next question because after all, the C explanation of LDI does say that the program counter is supposed to auto increment again. So now we analyze this part of the circuit. The first question is the program counter going to update? Because if the program counter is not going to update, then we really shouldn't be asking any further questions, right? So what do you think? Is the program counter about to update? Yes, it is in fact enabled, okay? If it is going to be enabled, then we need to track down this multiplexer, okay? Which input is selected with the multiplexer that is going in to the D port of the program counter? 0 is selected. Okay, so 0 is selected, which means we are coming from the adder. But the adder has the ability of not actually adding. In other words, we have the ability of staying at the current value. So the question now is, are we adding? Well, it is kind of obvious, right, that we are adding. And that's because PC Inc. and also address mux, they're both 1s. And this is an OR gate, which means the carry input, or K0, is going to be a 1. So we are in fact adding 1 to whatever the program counter has, and then that value is going back to the program counter, and the program counter is ready to update to become 02. Is that okay? So we double check, okay? We want to double check, make sure that it really is the case. And this time it's easier because we can just poke this wire, and it does tell us that 02 is on the wire going into the data port of the program counter. Is that okay? So when we have a rising edge, then we have two registers updating at the same time. The program counter updates from 01 to 02, and then the register B inside the register bank is going to update from whatever it was to 44 in hexadecimal. Is that okay? So when you go back to the C notation, we are now accomplishing both. We're updating B with whatever the program counter is currently pointing to, but at the same time, we're also going to increment the program counter. Are we okay so far with this analysis? Okay, so we do a Control T, and after the Control T, you can see the program counter is now 02. And then when we go into the register bank, or we can observe from outside, we can see register B is now 0100, 0100, which is 44 in hexadecimal. So we got all that done. On the falling edge, the microcode pointer is going to update. So in this case, the update is going to be based on input 1 to this multiplexer because the select is a 1. So this goes back to an adder, and this adder is always adding 1. There's no way to turn off that particular adder. So the microcode pointer is going to go from 6D0 to 6D1. Is that okay? But it's not going to do exactly that. When I do a Control T, it goes back to location 000 because the second, or I should say the content at location 6D1 of the ROM is only having the most significant bit being 1, which goes to the reset. Okay, it goes to this OR gate. It becomes a 1, and then this 1 is going to 0 the microcode pointer. So that's why we reset the microcode pointer back to location 000. So we are now ready to fetch the next opcode, which is the content of 01 at location 02 in RAM. Are we good so far? So this is the whole instruction execution cycle of LDI. Are we good so far? Yes? Okay. All right. Let me see. We got plenty of time. So this really helps with your lab today, because your lab today, is about the LDI and then the ST and the LD instruction. Okay. All right. So now we switch gear and we go back to the assembler. Okay. And we're going to do something here with the assembler. So what we'll do is we'll introduce the concept of a label. A label is a bookmark. Okay, I probably need to change the terminology of this class because you guys are a generation where you grow up with bookmarks in a browser, as instead of what we call a label in programming. How many people got introduced to the concept of a label in C and C++ programming? Nobody. It's a good thing and a bad thing. It's a bad thing because now I have to talk about it. It's a good thing because you cannot write, well, okay, I shouldn't say you cannot, but it'll be more difficult to write spaghetti code. Does anyone know what is spaghetti code? Were you guys introduced to that term? Okay. Spaghetti code? It's the kind of code that you produce once you become a Pasternarian. Once you believe in the flying spaghetti monster. Pastafarian, that's it. Thank you.
It means if you write code somewhere, something else, somewhere on the code will break.
Yeah.
If you don't do it correctly.
It means you didn't comment your code either, usually.
No, commenting does not have anything to do with spaghetti code. So spaghetti code is a pejorative phrase for unstructured and difficult to maintain source code. Spaghetti code can be caused by several factors such as volatile project management, lack of programming style rules, and insufficient ability or experience, or all of the above. Okay, so if you guys are wondering how bad can it be, I'll give you an example. This is real, okay? This is back when I was working in industry. So we were working on a compiler. I have a compiler background when it comes to software development. And the compiler was written, for CPM, which is a really old operating system. But nonetheless, it is still inspired by Unix. Anyway, there was one subroutine in C that has 600 lines. Yes, you heard me right. One single function in C, and it has 600 lines. Okay. Now, if you structure the code right, okay, 600 lines may not be too bad. Unfortunately, it has a lot of go-tos and labels. Now, go-tos and labels are exactly what it implies. You can define a label somewhere within the function, and if you say go-to and then the label name, execution will continue at the label. There's no restriction whatsoever as long as you're in the same function. Okay? Most people use this mechanism as an escape hatch. In other words, you're deep into like a conditional statement inside the loop, which is inside another conditional statement, which is inside the switch, which is inside another while loop. And you say, uh-oh, this is a really bad catastrophic condition. There's nothing I can do at this point. Then you just have a go to an error handling routine or part of the logic, and you just go like, I'm giving up, I cannot do anything about this, which typically is followed by the program exiting or generating an error message that is unrecoverable. But this particular function was not written for that, so it has go-tos everywhere. It would have a go-to from inside the loop, inside the conditional statement, inside the loop, into another nested conditional statement that is inside another loop, inside another conditional statement. So it's going from nested structure inside one nested structure into deep inside another nested structure. It is bad. It was very bad. I was not able to figure out what the function was supposed to do, and I just rewrote the whole thing as like 30 different subroutines. So that's spaghetti code. The result of writing spaghetti code is it is not maintainable, and it can also have a lot of errors. This particular program also made use of a lot of global variables. Okay, so global variables are bad. Okay, just repeat after me. Variables are bad. Every morning when you wake up, you chant that. Okay, you say global variables are bad. Okay, because with global variables, the worst part about using global variables is you don't really know which subroutine will change that. But then you can say, but we can pass things by reference, right? I can take the address of something and pass it along to a lot of other subroutines, and those things can eventually change something. But yes, you still have to take the address of that thing at some point and then pass it along as a parameter. So you still have a way to track it down and go like, okay, somewhere that this function can call, some of the other functions of this function may potentially change this thing. You can track it down. Global variables cannot be tracked down unless you look for the name of the global variable itself. Okay, so if you have spaghetti code combined with global variables, you have the perfect mix of basically unmaintainable code, which was great. I got job security. And by the way, I did not write that code. Whatever code I touch, I turn it into properly written structured code with no global variables. It took a lot of hard work to do it, and my boss didn't like it. My boss kept telling me, Tech, why are you wasting your time doing this? I go like, because I cannot understand this code, and I cannot work with code that I do not understand. But it's already working, just leave it alone. No, it is not working. That is why I'm changing it. What do you mean by it's not working? Norm, look at this, okay? Your compiler does not check the type of pointers. Okay, so quick quizzy here, okay? What is the downfall, or what are some of the potential bad things of not checking the type of pointers? Exactly. So let me give you an example, okay? For people who do not understand what I'm saying, if I present this as an example, you will know what I mean. Okay, let me switch to here. Okay. So let's say you have a function, okay, f, and somewhere you pass along struct xyz p xyz, okay? So this is a pointer to some xyz structure. And then inside the code here, you have char star ptr, okay? So the compiler was able to do this without generating any warning or errors. And why is that bad? My boss said, a pointer is a pointer, it's just an address. So why do we care what it points to or what kind of things it points to? Why is this bad? Mm-hmm.
It could spill over into other parts of memory if it's too big for where you're pointing it.
Right. So in this case, it is not as bad because we're taking a pointer that points to something potentially really big into something that only points to 1 byte. Okay. But if it's the other way around, it can be very bad because you will be using a pointer that is supposed to only point to a single byte. And you're saying, no, we look at this as a pointer that points to a huge, gigantic structure, and we want to access this particular member down there. Okay? And now, does it mean that you cannot do this in regular C and C++? No, you can absolutely do this. But the compiler will give you an error. So in order to tell the compiler, yes, I know what I'm doing, just let me do it, you have to cast it. Now, this is the best part about C and C++, is it does do some sanity check. It will say, are you really sure that's a good idea? And if you say, yes, I know what I'm doing, okay, it will let you do it. It's like, okay, it's on you now. You can even do something like this. This is actually even worse. You can say the pointer was originally a const pointer, and you can cast it to a non-const pointer. Most compilers will take this and go like, are you sure? If you say so. Huh? Okay, so this is funny because there was one class that I was teaching. I was trying to remember which class it was. It was an Android class. I was teaching an Android programming class, and one of the people in the class actually contributed code to the Android code base, with the Motorola phones. And it gave me an example of some driver code that did something along this line. And that was the reason why that particular phone could not connect to certain specific Apple routers. Because it would step onto this code. So with other routers, because of the way Apple routers do things, with Wi-Fi routers, only Apple routers would trigger that piece of code. So it did not connect at all to Apple routers at the time, and it was because of some code that looks like that. Yeah. Yep. All right. So getting back to where we were. Okay, so are there any questions about pointers? But in assembly language programming, there are no types. So you are definitely open to do all kinds of weird and bad things. Are we doing okay so far? Yes? Okay, so this whole discussion was originating from the discussion of labels. Okay, so what we'll do is we'll start to write the program, or we'll modify the program so it will start to make use of labels. So let's see, where is the tab? Right here. Okay. So now we'll do a label, and then we'll do a directive here. Okay, this is a byte. So after byte, it is an immediate, which means you can use a postfix expression, just like you can use a postfix expression in an LDI. So you can say byte. Okay, I'm not going to get too fancy here. Let's say 27. Okay. All right. So let's explain what these constructs are. So in this case, line 3 is a label definition, L1 with a colon. Okay. So you need a C type identifier with a colon right after that. that becomes a label definition. You can look at a label as a bookmark. Okay, so I'm inserting a bookmark right here. So now the question is, which byte is it bookmarking? Is it bookmarking the halt instruction, or is it bookmarking byte 27? Which one do you think is bookmarking? Because it's bookmarking byte 27 because we read from top to bottom. Okay, so it's bookmarking whatever is defined right after that. Is that okay? So what a bookmark is exactly the same thing as a bookmark in a browser. Okay, so what does it mean? Okay, so I'm just gonna go through this exercise here, and I say I want to bookmark this page, and I think that's the bookmark, right? Oh, this is to show bookmark. How do I add a bookmark? Right here. Okay, so when I click on this little star, it's gonna say, okay, I'm gonna bookmark this page. What does that mean? I mean, you guys, sorry, go ahead.
Come back to it.
You can come back to it later, but what is it doing? What is it remembering? The URL, which is an address, okay? In other words, when I insert a bookmark, the bookmark itself can have a name, right? So let me just do this. So Control D, okay, click on this, and I have a name. So a bookmark has a name so that I can go through all the different bookmarks, and I can look at the names, and I can go like, oh, this is the assembler, okay. And associated with this assembler name is the URL of this particular document. Is that okay? All right? It's the same thing. L1 is exactly the same thing. L1 itself is the name of the bookmark. And you cannot use the same name more than once inside the same program. Does that make sense to you? Because otherwise you go like, well, I need to refer to L1. Which L1 are we talking about? That doesn't seem to make sense. Yes?
So what does the assembler assign to it? Because I don't think it would assign L1, it would assign like a hex.
It will be the address of whatever is defined after that. So in this case, L1, it's going to be the bookmark of the address of byte 27. Okay, so which I'll explain next. Okay, so byte 27 is exactly what the name implies. It is going to reserve a byte, okay, and it will initialize the content of that byte to the bit pattern of 27 in base 10. So 27 in base 10 is going to be 16 plus 8 plus 2 plus 1, okay? So the bit pattern is going to be, let's see, there's a 16, which is a 1, there's an 8, so it's 1, 1. So it's 1, 1, 0, 1, 1. So together it would be 0, 0, 0, 1, 1, 0, 1, 1. Does that make sense to you? Because it's 16 plus 8 plus 2 plus 1. Okay? Or did I get my math wrong? No, it's right. Yep. Okay. So in hexadecimal, what is 27 in base 16? It's actually pretty easy. How many 16s do we have in 27? 1. So that's the most significant digit in base 16 is going to be 1. How much is left? 27 minus 16 is 11, right? So exactly, so we have B. So 1B is going to be the hexadecimal representation of 27. Is that okay? So hexadecimal 1B is in base 10, 27. Now, why is that important? Because we're going to switch to the assembler view so that we can see what is being generated by this code. So we switch to the assembler view, and we can see at location 0, 0, we have the 6044. I think we got that explained. Yes? Okay. And at location 2, we have the 0, 1, which is the halt instruction. I think we got that too. The label L1 does not generate any additional bytes because it is just a label. It is a bookmark. Is that okay? So when you define a bookmark in a browser, does it generate an HTML document? Nope. You're just saying, okay, this is the URL. I might need to come back to this place at a later point. Is that okay? So that's why the definition of a label on line 3 in this case does not use up any bytes at all in RAM. Is that okay? Now, byte 27, on the other hand, basically says, I'm going to reserve a byte and initialize that byte to the bit pattern of 27. Well, what does it generate? It takes up 1 byte at location 03, and it generates the hexadecimal representation of 1B, which is 27. Is that okay? So this is how you can spell out exactly what byte sequence you want to use. Why would we want to do something like that? For instance, if you want to spell out a string, okay, then you have to do it character by character. Unfortunately, I do not have a quicker way to define a string, but that's one way to do it. But the biggest question is, then what is L1 defined to? L1 is defined to 3. Is that okay? Yep.
So L1 is 03, not 1B.
L1 as a label, which is just a symbolic name, every time you refer to L1, it really is just 3. Is that okay? Now you guys would go like, no, I don't believe that.
So, yeah, I know it's an address. I'm just trying to double
It's the
check.
location.
Is it 3 or 03?
It's the same. It's a value,
Hex,
right?
Are we in decimal?
It's the label is an internal thing to the assembler itself, so we don't really care about internally how it is stored. It is however it is storing the value of what we know as this. I'm not even saying the word, because if I say the word, I'm implying a particular base. I'm just pointing out the quantity, which of course to people who are only watching this class through the video is not going to get at all. I'm sorry to those people. No, I'm not. Is that okay?
Come to class.
Yep, come to class. Exactly. So, but is that okay? This is a quantity, it's a value. Now, if I say 3, it's an implied base 10, okay, which is not what I want to convey, because we don't really care how Google Script is internally storing values. Now, as it turns out, it's just base 2, okay? But I don't want to use that because it doesn't really matter in this discussion. Is that okay? Okay. All right. So to make this program a little bit more interesting and to verify that L1 is in fact 3, I'm going to say byte L1. Okay, so what does that mean? I'm reserving 1 byte, right? And I want that byte to have the value of L1. So now the question is what is going to be the content of this byte? Now first let me press enter first, just to make sure that this can be resolved, okay? And it is resolved. But now the question is, what is this byte over here? We know the location of this byte is 04 because the previous one is 03. The question is, what is the content at location 04 according to this program? What do you guys think? I think there are only 2 choices, right? It's either 03, which is the address of the 27, right? B, which is the hexadecimal version of 27. So which one do you think it is? 03. 03 is the correct answer. Okay? Because L1 as a label, remember, it's a bookmark. When you refer to a bookmark, it's a URL. Okay? It is not the HTML document that the URL is pointing to. So when you go to the assembler, the assemble tab, you will see that location 04 in fact has a content of 03. Yep.
So can labels be used like variables to make the code readable?
No. There is no concept of a variable in assembly language programming. Now you can reserve a bunch of bytes, okay? But it's just a bunch of bytes. So how you use those bytes is entirely up to the code to decide. So there's no such concept as a variable. Okay? Yep, go ahead.
So it's basically the difference between a pointer with an asterisk and a pointer
pointer.
So instead of pointing at
Correct.
the content in the address is pointing at the address itself. The labels.
The labels are, in this case, the way we define this label is it is defined to be the address of whatever is following it.
Yeah.
So when we refer to the label itself, we're only referring to the address and not the content at the address. Yep. So are we good so far with this? Yep.
Are we then initializing label 1 with byte 27 as well as byte L1?
Say that one more time.
Are we initializing the address of, let me rephrase it. Are we initializing bookmark L1 with the address of byte 27 as well as byte L1? If that makes sense?
Okay, so to answer that question, the first thing we have to remember is in this architecture, it is byte addressable, which basically means each byte has its own address. The label can only be the address of one location, which in this case is the location of, it's the address of one byte. Line 4 is 1 byte. It has the content of 27 in base 10. Line 5 is another byte, which has the definition of label L1. Those are 2 separate bytes. So that means L1, when we define the label L1, it is the address of the 27, but not the L1. The L1 is the byte after the 27.
Okay, so are we initializing it to byte 27 then byte 21?
No, it's not initialized. It is simply defined to be the address of byte 27. When you look at this part here, it's more clear. You can see that location 03 has a content of 1B in hexadecimal. Location 04 has the content of 03. The label itself is defined to be 3, right here. So that means every time you see L1, it's the same thing as seeing 3. Are we good?
Okay.
So what can we do with 3 as a value? It's a very general question. What can we do with it? Can we multiply as a value, as an integer? Okay. So what if we say L1 and we want to multiply by 2, and then we can divide it by L1, right? Because L1 is just 3, right? Okay, this is a good test to see whether you guys can see what this is going to do. What do you think that's going to do? It's postfix notation, right? So L1 2 times is really just saying L1 times 2, right? So that is going to be pushed on the stack. So we have L1 times 2 on the stack, and then we push L1 on the stack, and then there's a division. So with the division, it will pop 2 things from the stack. The first thing it pops becomes the dividend. The second thing it pops becomes the divisor. So what do you think is going to be the value of this entire thing? Just 2, exactly. So let's see whether that works out or not. So we go to assemble, and here's our 2. Okay, but does that illustrate what L3, L1 really is? It's just a symbolic name of 3. That's all it is. Yep.
I'm a little confused because it seems like byte's able to take labels as well as constants like 27.
Because a label is nothing more than a symbolic name of a value.
And what I was wondering is so can constant numbers be turned into labels like 27?
Aha. Okay, so I like that question, and the answer is yes. Okay, it's a new construct. I haven't talked about it, but yes, you can. So if you want to define 16 to be 16, that's how you do it. So you use the C identifier. Okay, 16, spell it out, SIXTEEN. A colon. The colon is important because the colon says I'm defining the label. I'm not referring to the label. Okay? And if it is empty, after that, it becomes whatever the location of the next byte is. But if you say, some expression here, then it becomes the value of that expression. So in this case, 16, as spelled out, is going to define to be is defined to the value of 16. So when you go to assemble, it doesn't show, but if you refer to it in some other code, okay, so the next line is byte 16.
Why is there a colon there?
Oh, I shouldn't need a colon.
Would that change the
Well,
little
okay,
byte
what this
to be-
does is it defines a label called byte in this case, which is also defined to be the value of 16, which is not what we want. Okay, there we go. So now we go to assemble, and you can see how this particular byte here has a content of 10, but that's in hexadecimal. In hexadecimal, 10 is in fact 16 in base 10. Is that okay?
So the constant itself can't be 1, but we can make a label
Yes.
with strings that turns into a
If you want to. If you want to. But the most common use of a label is to use it as to bookmark a location in RAM. Okay, now why we haven't talked about jump instructions yet. So so the most important reason for a label's existence most of the time is it defines a location so that we can jump to that location. We can continue execution at that location. Like a loop or conditional statement or subroutines. So jumps are very useful. So we are almost running out of time, but I do want to answer this particular question. Okay, so I can say confused is defined to be confused. Isn't that funny? Because I'm defining a label, and it is based on itself. It's a cyclic reference, right? And if I press the Enter key, it will say, what did it say? Symbol reference cannot be resolved. Now it doesn't say it's cyclic. It just says I cannot resolve it. Okay, and so this is okay. There's a lot of dark magic involved to get a spreadsheet to do what it is doing right now. But the dark magic is not exactly dark because it's open sourced. So anyone who's interested in knowing how this is all done, including how postfix is parsed, you are more than encouraged to look into tools, script editor. And this is all done in Google Script, which is basically just JavaScript. So this is JavaScript that makes use of the spreadsheet itself, along with some other custom code that I wrote in order to parse like postfix and resolve symbol references and stuff like that. So that's you're more than welcome to take a look at this stuff here, but I may not be able to have time to explain it. Okay, so you kind of have to read and try to understand that by yourself. Now there's one more tab here that might be useful. See this tab here? It says symtab, which is the abbreviation of symbol table. Okay, this is where my background in compiler comes in really handy. Because look at this look at this cell here. It looks. What does that look like to you? I mean, some of you probably have some experience programming in Java, right? So what does that look like to you in Java? It's JSON. Very good. Who said that? Good job. This is JSON. So I'm just using a JSON representation that says this is label L1. It is defined on line 2. It refers to nothing, and the RPN result of computing is 3. So 16 is somewhere here. So the label 16 has the following object associated with it. The line number is 6. It is defined on line number 6. It has no references anymore because it's all resolved. And the RPN calculation is just 16. So RPN, is an intermediate kind of thing. If it can, so internally, RPN is basically just, I work on the RPN step by step until it becomes a single value. So if you're interested, you're more than welcome to look into the Google script. If not, you can just use the assembler as is. But I am totally abusing a spreadsheet. All right, so we are running out of time today. I'll see you guys over at in the lab, and I'll close the